on Wednesday, I'm supposed to have we're supposed to do a luncheon that I may not make back in time for class. It's supposed to go till 1. And it starts like at 11:30. So right after lab and right before lecture, let that stand. I can make the time to make sure I'm back by 1. And obviously I can leave by 11:30. Now my son, who's your age, came up with actually a pretty good idea. Why don't you shift the lecture on Wednesday to lab? I know that doesn't help you, but on the other hand, because we're just literally we'll be wrapping up, I don't know what we're actually, but depending on what we don't get to today, we might be wrapping up Lagrange. Okay, and then we'll be jumping into path planning, or path motion, I should say. Motion profiles, paths. So we're starting to get to that last section of material. And I can be here at 1, but if we wanted to move the lecture to the lab session, we can. And I can reduce and shorten the amount of material for computer vision as well. If that's good for all of you guys.
Yeah.
So if you guys want to do that, then we don't have lecture. We still have lecture, but we just don't have it at 1 o'clock. And then that alleviates the log jam of leaving at 12:45, 12:15, trying to get back, find parking, and that doesn't happen. It's 15, 20 minutes away. So that's the potential I see as that being impacted. But if we did the lab thing, it's a pretty good idea, I thought, actually. For you it doesn't work for you. But you can just come to class at 8 o'clock instead. You shouldn't have a class conflict. The other thing we can do is we could do class at 9, start at 9, and go 9 to, like, say 9 to 11, do a computer vision and wrap up Lagrange. Do whatever's remaining, see how it goes today. But I want to throw that out there for you guys. I'm okay doing 1 o'clock and just leaving the luncheon early. But, yeah, there's options. Are we all good with the shift day? Because you're supposed to be there for one of you, except you're supposed to be there at 8 o'clock anyways. So you're supposed to be there. I don't know if we want to start at 9, if we want to start at 8, and if we finish early, then great.
Can we do it 8?
Yeah, I think that might be better, and then it gives you guys time to work on. I don't want to take time away from the robot, but here's what it is. The hour and a half that we do for lecture, you're not losing that time. We're shifting when you're working on it, that's all. You just won't be in the lab. That's the downside. So I'm pretty sure there's a class or a lab in there right now. So you lose access to the lab. So that's where the penalty is. But if you're working on resources outside of the lab regardless, then it doesn't make a difference. So what do you all think? Are we good? Yeah. Okay.
I can share the video.
Oh, yeah. Yeah, share it, that's fine.
Yeah.
Everyone do that. Okay, so we're good on that? Now, is there anybody, I'm supposed to take a poll. Everyone's good with shifting the time. Is everyone good with that? Actually, if you're not in favor, raise your hand.
You are not in favor?
Huh?
What's the proposal?
Oh,
So Wednesday, we start at 8 o'clock, and I lecture the lecture material during lab. Then we talk about computer vision, but I don't go into much depth. So I'm just going to go through the theory of computer vision. I have different examples. I'm going to show a simpler example using how to walk through the stack of how to do computer vision for object and scene recognition.
So you don't use this time computer vision
No.
in the morning.
No. 1 o'clock is moved to 8 o'clock.
you're going to have class at 1 o'clock.
Oh, okay.
So there's no 1 o'clock on Wednesday.
Yes.
Yeah, computer vision.
No.
No class Wednesday.
No.
No,
We're gonna move it to the lab.
8 o'clock time frame. So the hour and a half we have for class, we're going to use in the lecture.
lab.
We're using the lab.
So just combine the two, so we just start in the morning?
Yes.
And then you have the hour and a half now, 1 o'clock, to do the lab.
To do the lab. To work in the robot.
Okay, yeah, that's fine.
So we're just moving the time on what we're doing. We're not losing time. We're not I'm not canceling class. I'm simply shifting what we talked about when. So the activity for lab is gonna be done during this time, so that the luncheon, I don't have to leave early for and everything else.
Gotcha.
Does that make sense?
Yeah, I get you.
So,
Oh, I didn't know you had a luncheon. Okay, that makes sense,
oh,
yeah.
you walked in late. No, you didn't.
No, I didn't. I was just looking at my exam. I was paying attention.
Oh, paying attention, I did that, there you go. That's
Yeah,
all.
that'll do it.
I'll do it.
All right, so we're good, 8 o'clock on Wednesday, we'll finish up Lagrange, go into any kind of path planning, and talk about computer vision and how it would work for robotic detection. We won't go into I stopped doing the computer vision kernels, because that's really better for computer vision class. But we'll talk about the other aspects of it, and how to do it, and what you use for scene and object detection using the other code set that I've got. It's really the procedures, and I want to show you the different procedures that I've already got done. Are we all good then? Anybody walk in that still did not get their exam back? Yeah. They got 4 of them. No?
What are the names?
Not Robert. If you don't have your exam, then you know. Okay. So let's talk about Lagrange. And those, you guys, I posted those files, yes? You all have those? Did you guys get the scores for the exam? Okay, I'll figure out what's wrong. Okay. Don't have reading this weekend. All right. I really don't like Canvas. Who was in the class where Canvas ate their homework exam? Was it? Yeah. Canvas. You know what's happened? That happened to my son's professor. He did the same thing I did, made an adjustment so someone else could take the exam at a different date, and it just corrected all the test scores. So my son told me what happened, and he told me what happened. I go, believe it or not, he thought he was joking. I go, no, I've had Canvas eat exams that were submitted.
That's true. Sorry.
Well, they're talking about me, but not just me. It was somebody else.
I remember that happened to us in
Microprotocol. Yeah, that happened in my son's class too. The professor made the same exact class assignment. I go, yeah, it happened. It's a flaw in Canvas. So I thought they would fix it, but apparently not. Okay, did I say it on the Canvas? Blackboard was so much better. It didn't look as nice, but it was just functionally better. Which is usually all right, enough of that. We're looking at that stuff. So we need to go to. Everyone have a good weekend? Yes. Productive? Yes. Everyone's arms coming along? Remember what slide? I think we're on slide 16. Yes. All right. So kind of like recapping, the idea of using Lagrange is really where we can circumvent doing the detailed Newtonian analysis, and instead we're going to be looking at it from an energy perspective. And we looked at it here when we were talking about this pendulum with a cart, where we looked at the force, and we could look at the torque. And so we're looking at those different variables. And the process of doing Lagrange really was we compute this L, which is the difference between our kinetic energy from our potential energy. And we write the terms of our kinetic and our potential energies for each one of these entities. So we're looking at it in terms of the force and in terms of the torque. Once we find those, then we're going to take this L, which is that expression, and we're going to take the partial derivative with respect to theta dot, which is really the velocity that we've been talking about. And so that's our motion. Think of that as our motional force, or the force per motion. And this is our potential. right? So then we're taking it with respects to not the velocity, but with the quantity itself. Okay. Because we're looking at this right here, we then take the time derivative because we're really looking at the velocities. So we're looking at velocities relative to a particular parameter. That's the idea behind taking this one there. So we have this relationship of L, and we have this relationship of L. So we have this one and this one. So here is our P, here is our K. We do that for both types of quantities. So we're looking for the force of this and the torque exerted on the pendulum that we had right here. All we have to do is write those expressions. Once we do that, we can combine both of them together so we can express the relationships of the two energies through force and through torque, and we have the Lagrangian relationship right here. If you decided to do this using Newtonian, this would work too. You get the same answer. One's a little bit easier in the sense of it's much more methodical. This is a methodical approach. You kind of like just do it, and you go through and you take the derivatives, take the partial derivatives, take the partial and the derivative again, and you're good to go. Okay. Any questions on what we were talking about on Wednesday last week? It's pretty straightforward. Yeah. Because we can talk about this double pendulum. In the double pendulum, we were talking about, if we look at it, it was really, if we flip this upside down, almost it looks like a robot arm that we talked about before. Right? I think we've done that before. So we could use that same process. And so initially we'll talk about it as a pendulum, but at the end of the day, it doesn't matter if it's a pendulum or not. It's really got these couple of joints. And we can do 3, 4, 5 all the way down. But again, we go through that same exact process. Write the expressions for our K's, write the expressions for our P's. Find L, nothing more than K minus P. Take the partial derivative with respect to the changing variable for each component. So we would do one for theta 1, we do one for theta 2. That gives us these two masses. We then take the time derivative of the one that we took the partial derivative of from this guy. Take the other partial derivative with respect to that component. Repeat for all variables. Okay. So we just kind of do this over and over and over. If we had 3 joints, we would do this 3 times. Theta 1, theta 2, theta 3. If we had 4 joints, we would do 4 times. Theta 1, theta 2, theta 3, theta 4. So on and so on. Yes, it gets tedious. I'm not going to deny that. But we can actually write code to do that kind of stuff for us. So we can actually find the Lagrange from a computational perspective much easier than just going through trying to see this big picture, doing the Newtonian, doing all the free body diagrams, yada yada yada. It gets tiresome. So here's what we have right here. So in our double pendulum, we're going to have our kinetic energies. And that's what we have in this case. So we have the one with theta 1. And then we have theta 2, which is really a combination. This is a combination of this angle and this angle. So if we're looking at the force on the mass or the torque on the mass, we have to recognize there's a common element of theta 1 and theta 2, not just theta 2. So we see that double angle that we see right here. So we see the one by itself, and we see the combination of those two. Everybody with me so far on that? So we're looking for the kinetic energies, so we find the K1, the K2, here's how we find that. And we're going to get each one of them. And in this case, we actually found a velocity squared, and we'll see why in a minute, but it's and 1/2 mv squared is the reason why. And that allows us to simplify in the future. You'll see that on the next slide after this, the following one. We can then sum the 2 Ks. And so this looks like a lot of variables, but at the end of the day, what we've really done is found K1 and K2. And if you look at it, we can see, yeah, we really have, because here's this guy, right? Then here it is with the double angles that we have right there. It's just written out. Everybody good on this so far? We do the same thing for potential energies, which is MGH. So we have here P1 and P2. Again, we can do the same thing with the cosine of that angle. So again, it's how much mg is going to be with a function of cosine theta. Here it is the double angle, theta 1 and theta 2, which is exactly what we see right here. And so we can write each one of those. So there's our P. This becomes our resulting L. So once we know our K, once we know our P, we can find L. This is the Lagrange expression, that whole expression. Again, it's not hard. It tedious. But tedious isn't that bad. I mean, if you go through it over and over again, imagine you have this for a 3-link. You got a whole bunch more over here, right? 4-link would have a big bunch of lines. But at the end of the day, it's just kind of copy and paste or rinse and repeat with each one of the various angles. All right, so once we have L, we take that partial derivative with respect to theta dot. Then we take the time derivative. So that's what we have here. So we're going to take that partial derivative for K1. And then we're also going to do the potential energy as well right here. So here becomes our torque. He's got a little small, I'm not sure why. Let's make him bigger. Microsoft equation working for us. Didn't get bigger, did it? All right. Well,
You gotta change the font.
in Microsoft equation, usually you don't do that. But anyway, spread them out a little bit. I can get that font bigger. See, I don't know if I can do this one, can I? There we go. Yeah, yes. Anyway, math isn't too hard on there. I think you all agree it's pretty straightforward. Yeah. Any questions on how we got any of these expressions? So that's torque 1. So that's the one that's acting on this pendulum right here through theta 1. Then, now that we've got that expression, we can do that for each torque, and we can actually construct them into the matrix. So we can do that. Here's 2. I think I skipped 1. So there's 1. And that's kind of the same thing here, but now we're doing that for 2. Right, so here's dt of partial with respect to theta 2, and then this is take the L, take the partial with respect to theta 2, given the L that we had. So again, we're starting off with this L right here. And there's just simple calculus. Everybody with me on that? So we go through, we do T1 and T2. We can matricize both of them and extract our variables so that this becomes the relationship for this guy, theta 1. This is for theta 2. This is the 2-part for theta 1, and this is the 2-part for theta 2. Notice the torque 1 is going to have this component, right? It's got this guy right here for the theta 1. And then the theta 2s is just going to have these guys. And what's interesting is here you see that this only uses the theta 2s. And then we've got this expression right here. So this is actually like our angular, this top one is like our angular acceleration, right? That's going to be theta double dot. We know that theta double dot is an acceleration of the angle. We could have called it alpha if we wanted to, but we'll call it theta dot double dot. What we see right here is the square of a velocity. And that's like an acceleration, but it's not quite. And same thing over here is like an acceleration, but it's not what we think of as a rotational acceleration. There's something else. As it's increasing the velocity, we see that it's growing. So it's not in the truest sense an acceleration, but the velocity is growing at the square. That's the contribution of that torque. And we see that same thing here, except now what we see is the velocity of each component impacted onto the torques, torque 1 and torque 2. So here's this one applied to this guy, and then this guy is applied to that one. And then these guys, there's nothing on. And then finally, we get this last little bit. So if you think of this as the motion part, think of this as like the motion part. So here's my acceleration. This is something that's a result of the velocities directly from theta 1 and theta 2. This is a component between a coupling of the two velocities. So as this is spinning at a velocity, and this is spinning at a velocity, what is their combined velocities doing to it? And then down here, we look at that and go, well, that's like the potential energy still. That's the potential force that's applied, because we see the gravity component. Here we just see masses, we just see the length. So as this thing is being flung around, as it changes as a function of thetas. This as it's accelerating, there's a torque applied. This is as it's rotating. So when you rotate something, I should have brought a yo-yo, but I'll do my own first.
Oh, no.
So as I spin this, there's a force, right?
Yeah.
It's pushing out, right? We call that centripetal force. It's constant velocity, but there's an angular acceleration nonetheless, right? We know that. Then there's that rotation if I had a mouse attached to a mouse, we would see that there's that guy, this guy hanging out over here, as it's swinging around, it's at a velocity, it's pulling this velocity with it, right? That's what this one's doing. All of them are affecting the torques, because pulling on it, right? It could be pulling on as a pulls on. That's this guy. Pulling on as a pulls on. So it's like a coupling term. Okay. And then this becomes basically the potential energy, how much we're flipping around from gravity. Pulls it back down, pulls it back down. We get into that periodic. All right, hopefully I can break my nose. No, we're good. Okay. So when we look at this, we see the angular acceleration. That's what we were talking about here. Plus the centripetal acceleration. That's the one that's pushing you back, right? It's the one where you get the carnival ride and spin around and it forces you up against the sides, right? We've all done that and then thrown up when we got off the ride, right? I never did that. I was like, I'm not going on that. That stinks. You throw up on that all the time. Then we have this Coriolis acceleration, which is really a frame going around the frame. So if I had this one spinning over here, as this was spinning, it's the one spinning around the frame, we call it the Coriolis acceleration. And then we had basically the potential energy or the gravity of that. All right, double pendulum, make sense? Yes, sir.
I'm just confused around the Coriolis acceleration. Since it's about the frame accelerating around another one, shouldn't there be values on that bottom half as well?
No, this time this plus this time this.
Oh.
Where would this go to? Yeah, no. Yeah. So we're really just looking at that and that and that to that. This to this plus this to this. And then there's no more. Right? There's no reason to have it. So what if we were to do this for a 2 degree of freedom robot arm? It looks pretty much the same, doesn't it? We just flip that inverted or that double pendulum upside down. We're going to have the torque about this axis. We're going to have a torque about this axis. We're going to have a theta. We're going to have a theta. We're going to have an L. We're going to have an L. Almost the same thing. The torque relationships will be the same. Okay. The expressions for P and K, yes, those will be different. But the structure, find L, well, find K, find P, find L, partial derivative, or take the first time derivative, theta dot, right? Theta for theta dot 1, theta dot 2. And then take the partial derivative with respect to that, and then we take the partial derivative with respect to time. The other one, we're taking the partial derivatives with respect to the theta 1. Do it again, take the partial derivatives with respect to theta 2. All we really need to do is understand what the forcing function is for K and P, for each one, which isn't really that hard. So that's what we're saying right here. Write the sum of all the K's, write the sum of all the P's, find out. Take the partial derivative with respect to the changing variable for each component, theta 1, theta 2. Using 4, take the time derivative of that partial. That's going to give us K. Given L, take the partial derivative with respect to that component. That's P. Repeat that for theta 1 and theta 2, theta 3, theta 4, etc. Rewrite them into a matrix expression. Done. Gives you everything you need to know. So if we look at the displacement, we can find the velocities. So we know that xd is defined by this, right? This is going to be L1, right? So here's L1 times cosine theta 1. And then this is the angle identity we did before. It's going to give us the compound angle cosine with 1/2 of L2. This is going to come from the moment of inertia. And for all the electrical people, just nod your head yes. For all you mechanical people, know that that's coming from the moment of inertia. Okay? Does that look familiar if you're from moments of inertia? Yeah. John says no. Yeah, man, I thought I was done with that class. It's come back and haunting me. But for electricals, that's the MOI. Okay? So that's for that structure. And so that's the idea behind this one. We do need to know the moments of inertia for that. Several ways to find those. I prefer the integral method, but some of you might have learned the triangle method or the add things up method. I don't know what you guys learned. For your moments of inertia, would you guys learn in MSET?
I feel we mostly saw those guys.
Okay. Yeah, use trig methods. It doesn't really matter.
I think the thing was strict.
It's all the same. A moment of inertia is a moment of inertia. It's like a mass, but it's not a mass. So that's what we've got right there is that 0.5 L2. That's the idea behind that. Center of mass is located. It's just simplified for this particular joint. Find the velocity square terms because life is easy when we find the velocity square terms. But we're going to find xd is going to give us our x dot and y d becomes y dot. So these are like velocity terms for each component in that direction. We can use those velocity square terms right here because we're going to find the velocities through this guy. So we can figure out our momentums, right? Our kinetic energies, 1/2 mv squared. In this case, we're not dealing with m anymore as a point mass in physics. Our m is now our moment of inertia. Okay, so that's really where that's coming from. So that's why we're getting this guy right here. That is our moment of inertia that we see right here, or our moment of inertia that we have somewhere there. So here's my v, 1/2 m v squared. That's my kinetic energy for K1, plus 1/2 m v squared with that angle in there as well. But IA happens to be 1/3 m1 right here. So this is our moment of inertia written out, and our moment of inertia written out. So far, so good. Again, you can see why I wanted to have a conceptual discussion. This gets really tedious. The process doesn't change. You may have an exam question, but I'm not making you go through and derive all of these. Okay? It'll be conceptual. Like, you know how we did the IK conceptual? We had to understand it, but I didn't make you guys derive the IKs. Why? Because, well, the software generally does a better job for you. Or like quaternions, right? Quaternion. We talk about why you do the quaternions. And I have you do the methodical, just do it by hand. No, I wanted you to understand the concepts. So you'll have a concept question on the grounds. We're not completely sweeping this under the carpet, but we are addressing it. Fair? Okay. So that's that part of it. So for our kinetic energy, we can clean this up and actually get it more into this terms where we've basically solved for all of or we've grouped all of our theta 1s, and we've grouped all of our theta 2s, and all of our theta 1, theta 2. So out of the book, this is the equation 6.9. Do the same thing for P. So we find P, and we're going to find for the coupling of P. So here's our coupling term. So we're going to find our potential energy right here, and then our potential energy right here. So this is literally right out of the pendulum problem. You look at it, oh, it's the pendulum problem, and say, yep, you're right, sure does. Except now we have a moment of inertia. We no longer have a point mass. We've now gone from a point mass to a length of mass. When we go from a point mass to a length of mass, we have to use the MOI, or the moment of inertia. We have to describe what that mass is. Even though it's elongated, there's that center of mass, and we said, okay, this is the point upon which it doesn't technically rotate in its own frame. The moment of inertia. So we do that.
So here's our K, here's our P, here's our L. So this is all of our L's. So this part is each term, our couple terms, and this is our P. But at the end of the day, it's just L. Everybody with me so far on that? At the end of the day, it's just L. Once we have L, we do the Lagrange. Take the derivatives in L to get each one. Right? So again, K is going to be the partial derivative or the time derivative of the partial derivative of theta dot. Find our potential energy by taking the partial derivative of L with respect to each variable of interest. Find the torque, which is going to be this guy right here. Kinetic minus potential. Everybody good so far? Has anything changed from the cart? No. Process has been identical. Yes, it got a little bit more tricky when we went to the double pendulum. And we went from the double pendulum to this one, again, because the double pendulum is point mass. Right? We know it's going to be centered right on the ball of that sphere. We don't have a sphere anymore. We actually have that arm as acting on the moment. But at the end of the day, we're still going to be left with the torque. So we do that again for both torque 1 and torque 2. Right? We solve both of these problems. And so this is symbolic evaluation tools make this easy. So once we can construct L, we can let the tools do the derivatives for us and let them do the calculus for us all day long. Not saying you have to. You can use the tools because you've already done your calculus class. That's the whole point of doing that. That's why I'm not going through and grilling you on this, because this is not a calculus class. I'm not grilling you on calculus. We could spend 3 weeks doing Lagrange. Doesn't anyone want to do that? I mean, we spent 3 weeks doing transforms.
It's a lot more fun.
But that was the reason why. It wasn't by rote. It wasn't turn the crank. You had to understand what was going on, wasn't it? This one is not like that. It's like, okay, I find K. In fact, once I found it, to be quite honest with you, this is literally the same thing. If I added another one and then I have LG, and I'd have this guy right here, L1, L2, coupled together for a third joint. It just chains together. Remember doing the chain rule in calculus? You had to do the one side, the one side, the one. That's all we're doing. We would literally just chain mass, the next one. But it's going to have that coupling from the prior two. So you'd have L3 over 2 sine 1, 2, 3. And here you'd have L1, L2 plus this, plus that times the M3G. That's it. So you could very easily write this in terms of iterative variables, of i's and j's, and just work through it, right?
Like summation?
Potentially, yeah. So yeah, this would be a summation term. So yeah, this would be the summation term. But it'd be a little bit trickier because that's kind of gross, but yeah.
Okay, I get you.
Yeah. So you could do it in iterative variables. You can begin to see the pattern. Once you can do that, that means we can compute it in the computer all day long, or we can do symbolic algebra or symbolic systems to do the problems for us. But we have to set it up to begin with. Once we find P, once we find K, it's a piece of cake. So finding P and finding K are the only differences. That's where your brain comes into play. Everything else, you can hand it off to a high school student and say, go find the derivatives of this. Right? I mean, that's really all it is. You've all taken calculus at your 1 and 2, your freshman, sophomore level curriculum. You're done. You've had calculus. You're going to do derivatives all day long. So I don't want to turn this into a derivatives class or a calculus class. This is why we're going over it at the pace we are, the way we are. So we can find T1, we can find T2, put them all together, and here's our T1 and T2, and we get this pattern. If we have a twist, it does change the orientation a little bit, but the process is still the same. Okay. So this is rotation. Now we say, well, what happens if I had an elongation? Now all of a sudden, I'm not dealing with a torque, but I'm dealing also with a force. So if I have, this right here was a double revolute. What if we had revolute and prismatic? Now all of a sudden I'm dealing with force on that extension and torque on this rotation. But that torque is a function of L, and that's exactly what we see right here. This again, just going through the same process. Here we have theta, that's going to be the delta R that we see changing. This is the change in radius. That's what we're talking about. So this is the acceleration of the arm extending out. It can definitely affect the torque, and it can affect the force. This becomes our primary accelerator. Then we've got the centripetal, Coriolis, and then the gravity. So it's the same process every single time. We can call them different things. The tricky part is just coming up with the initial K's and P's. That's it. And that's really a physics problem more than anything. Why do we care? Why? I mean, why? So what? Why do we care about what the forces are on our robot arms? Right? Holding torque. What else? Yeah, so if as we were talking about, and I did lateral raises this weekend, it was yesterday. I'm not sorry, that's good. So clearly the amount to lift this up is a lot less than the amount to lift this up, right? Because of that moment arm. As I'm extending out, the robot, unlike what your robots might be doing, generally the arms don't move one joint at a time. There's more fluid motion, right? So we're trying to figure out that path of what we're doing. We saw that in the IK, remember? When we were doing the IK on Coppellia Sim, the inverse of kinematics, we didn't worry so much about force. And on Wednesday, we'll look at that. We're going to go back and revisit that IK. You're going to see the force depending on how far it has to extend out. So I'll redo the arm, so I'm going to move it in, say, X and Y, and that arm's going to have to reach out, and then I'm going to move it up, and we're going to see it. Unfortunately, the IK doesn't let me do all three axes at the same time. But we're going to see that force change, because the arm's changing, right? It's changing these dynamics, and they're all very parametric to the overall design of the arm. Again, but why do I care? Why do I care? What did we talk about last chapter? When you're doing the homework on right now.
Jacobians.
We're talking about what?
Just differential
What was
motion.
We're talking about Jacobians, but what were we really talking about?
Differential motion.
Differential motion, which is, let's think about this. First chapter, chapter 2, was position.
Velocities.
Velocity. Acceleration. Well, we kind of control each one of those parameters, right? We have to be able to control the accelerations. Because if we try to accelerate too fast, to go from V0 to V1 in our differential motion, we can only get differential motion through acceleration, right? We can only get differential position, differential velocity through acceleration. So if my tip is moving along, and that tip is moving so fast that I've had to accelerate that profile, I know how much torque I have to exhibit in order to follow that, to get to that velocity. That's why we're talking about this. So to get to that velocity, I have to exhibit an acceleration. I have to exhibit a torque. Now, what if my motor can't produce that torque? It's all over, right? Now, let's take that one step further. Iteration 1. My robot can't exhibit that torque to get to that velocity. Do I go home or do I do something different? What do I do? Pick a different what?
Direction.
Not direction.
Geometry.
Not geometry. Not motor.
Velocity.
Velocity. Just don't go as fast. Or if I can't,
Oh, it's torque curves. Okay, that makes sense.
so which means, or maybe if I get stuff to get to that velocity, I accelerate slower. Because acceleration drives that torque. We know that, right? It's the acceleration cross the moment arm, or F cross, it's MA cross moment arms torque, yes? That's all we have right here. Here's the moment arm, L. Here's my mass. Here's my acceleration. There's my torque. All it is. However, there are other components as this thing is getting longer, or maybe that sub angle that we saw before is flipping around doing its thing. So it has a contribution to it. But at the end of the day, I'm trying to find out, does my motor have enough torque to get to the velocity that I want in the time I want to get to it at?
So for this, you would just like plug in your motor's like max torque.
That's right.
To then find your maximum.
And can I get there with the acceleration I want? If I can't get there, I either change my velocity and keep my constant acceleration, or I reduce my acceleration and take longer to get to that velocity, which is exactly what we talk about next chapter. Right? So far, we've only talked about constant, right here, this is constant acceleration. Now, here's the other question. When you guys get in your car to go somewhere, do you hit that accelerator and hold it at a constant acceleration?
Try to.
You hit somebody in the process, yeah? So, how do you drive it? How do you, when you get in a car and you want to go somewhere, do you accelerate constantly?
No, you're very
You
good.
feather the accelerator. You kind of like lean into it, right? You slowly take your foot off. So you're really working at the third derivative when you're driving a car. You're changing in the accelerator. You might even be changing in the fourth derivative.
Jerk.
No, the third derivative is jerk. Fourth is just the fourth. We don't have a name for it.
Oh, yeah.
You can say it's the Star Wars derivative if you want, but that's not very popular option. No one gets the joke. Made up fourth.
There you go. It's coming right now.
It's coming up.
Yeah, it is.
What happens in the circumstance that we have to have a certain velocity met, or that said robot arm has to travel at a specific
In
speed?
that time frame, then you have to make a better motor.
So that would-
Which brings up that point. So what if you can't do that? Then you need to change the geometry and design of the arm. So that's why we do the Lagrangian analysis. Does my robot have sufficient torque to get it to move in the motion profile desired or required?
So can you say we can also use Lagrange to meet design?
Exactly. So we would do the design in the class. You'd say, okay, here's all the stuff I have. Let's plug it through the design of the Lagrange. Let's let the Lagrange chew on it. Do I meet my torque requirements? So to make that robot move at that parameter, to give that kind of velocities that I need to have that accelerations, I need to have so many foot-pounds of torque. Does my motor give me that? If the answer is yes, then great. If no, then you say, okay, can I change that acceleration? Or, given that this is what I have, I can work it backwards and say this is the maximum acceleration I can use.
Reverse engineer back.
Right, you can go back and forth through all of these equations. Just iterating back and forth. So this is avoiding the Newtonian methodologies of free body diagrams with F equals ma. At the end of the day, it is still F equals ma, right? F equals ma. ma. Right? Force equals ma all day long. It's just a complicated way of writing it. But it embodies all of the other components. That is the interrelationships. Like we saw the Coriolis, or as this extends out, it changes. So this is a derivation for the polar robot arm where it has a extension and a prismatic and a revolute joint. All right. So far, so good. Theoretically understanding everything, right? This is where we're more theoretical in this portion of the class. Next chapter, we get very practical. They're kind of like balancing back and forth. So the general expression of the robot arms looks like this. So we have the plain old acceleration, our centripetal, our Coriolis, and our gravity. So you see I to JJ, these are the cross terms. So these are where their two are combined. This is strictly on the I, and this is strictly on the J moment or value. So this is for 2 degrees. If I had 3, then it would be a 3 by 3 and add more coupling terms. But this would be a 3 by 3 matrix, and this would be 1 by 3, and this would be a 3 by 3. And so we see here the centripetals are I to I, all of them are to each other. This is 1 to the j's, this is a single j to both of the i's. Really what's going on there. D is basically the degree, it's just some dummy variable. Coriolis, cross-coupling terms. And then our gravity effect. Gravity is a force that we have to contend with all day long. So this is how we get to that from the Lagrange. We can literally plug this in, get the values, and call it a once we know what each one of these terms are. These D's will be a function of the physical architecture of the arm. So far, so good? All right. At the end of the day, they're coefficients. Okay? That's really all they are. These are our expressions. This is a value. At the end of the day, this is just a number. It could be 2.7. This could be 4. This could be 99.25. I don't know. Okay, those are a little absurd, but you get the point. They're just numbers. Yes, those numbers are constructed from these relationships. And this is how we express them in math. But regardless of the arm, and regardless of the architecture, they're going to boil down to this structure right here. This 2 degree of freedom arms. So if we look at the Lagrange for the multi-degree of freedoms, we can chain the Lagrangian process for anything above the 2 degree of freedom. It can be done. It can be tedious. And the modern way to do that is to do symbolic tools. Use symbolic tools. Forms. Okay, so far so good. But is there a different way? As Din Djarin would say, this is the way. This is the way. Wait, there's another way. What? Imagine you're watching Grogu and somebody says, no, there's a different way, dude. Not just this is the way. There's one more way, too. What? Okay. Well, what can we do? Well, we can use the frame from each joint to describe the position from each joint to another joint. Wait, what? This sounds like remnants of chapter 2, doesn't it? I can use the frame here to describe to the frame here.
Sounds like a triple.
So, do I really need more than 2 degrees of freedom for my robot arm? Could I just do like these two? Okay, that's now those two are this one to that one. Those two are. I can just do 2. All I need is 2. 2 degrees of freedom. Does this say anything up there about planar arms? Does it say polar arms? No. What we saw from those first 2 structures is this was the same structure, wasn't it? Expressions are different, I would agree. You have to do that anyways. But once you do that, do I really need to do a 3 by 3 that I alluded to? No, I really don't. I can go 2 to 2, next chain all the way along, using successive frames. So I can use the velocity from a frame to describe the kinetic energy of that frame.
That was a lot of words.
Yes, it was. That's why this is a highly theoretical chapter. We could do the math, but we don't really need it. Lagrange for frames. Did I spell Lagrange? Yeah, we did. Lagrange. Lagrange for frames. All right. Dr. Bostovich, now what are you talking about? I thought we were done with frames. I got the K. I got the P. This piece of cake. I loved it. Right? So can we take what we know about the Lagrange and apply these Lagranges to frames specific? Say, look at the end down here as well, Lagrange. Can we take that? And the answer is, yeah, we can. So if we go back to the frames, man, thought we were done with that note. At the end of the day, a frame is a description of a position, yes? What did I just say? Position, velocity, acceleration, right? Position is a frame. It's a description of a point in space with a pose. It's got a direction and a location. It is a spot. It is a point. It is a D or an L. We can describe that. We can do right here. So, can I take the partial derivative with respects to a variable of interest? Sure, why not? So if I do that, take that partial derivative of theta, I get to this guy right here. And then I can decompose that one step further. And I see that, oh, wait a minute. If I have this modifier up front, let's call it Q, then I can describe this guy and this guy. Right? I can take some Q and transform this into this by that. Because that's just nothing more like a transform. A transform. It's a general matrix Q that relates the change of A with respect to theta from A. You go into your graduate level classes, you're going to see that equation all the time. I drew it on the board on Wednesday, remember? AX equals B, where B could be, or A dot. In fact, you're going to see this one a lot. You guys all see green on the board? Yeah. You might see X dot is equal to A times X. Now, in the controls world, these might be vectors. But what we're really doing is we're relating these two spaces by means of that matrix A. In this case, we're saying it's Q. So I can describe this guy to this guy through this one.
Oh, by transform.
Kind of like a transform. Transforms are actually just doing the same thing. We just gave it a special name and backed into this discussion.
So now we're learning where it came from.
In a way. No, we derived T's. We derived T's from scratch.
Yeah, we did.
But the concept extends. That's the point of getting at. And when you realize this, then you're ready for grad school. So you all should be going to grad school at the end of this class. Because when you do, you're going to see that all the time. And you go, yeah, I got this, no big deal. When I was a student, I was learning this, I was like, huh, okay, got it. Grad school. I've seen that before. No one told me when I was doing it in undergrad, but we're going to see it before. Why? But I'm telling you that. I'm giving you that little decoder one time. So now, again, we can look at a revolute frame that's been decomposed. That we have right here. That's basically the same thing, right? So a revolute and prismatic joints, we can create this modifier matrix Q to allow us to get there. Good? Yeah. Okay. We're almost at the end of this lecture set. We're almost at the end of time, which is about right. Which means on Wednesday we'll start talking about path motion, which is really good. We'll be done with chapter 6, Lagrange. Conceptual question. I don't really know what kind of good homework problems to give you out of the book. That's the problem I'm struggling with. I don't really want to give a bunch of busy work for the sake of busy work. Do you guys want busy work? No. Just like quaternions, so yes, well, what kind of question would it be? It'll be on there. It'll be conceptual. It'll probably be relating the problem to Lagrangian and how it affects and why, and blah, blah, blah. Something you can't just Google, because the Google or the AI won't know the problem you're applying it to. See how we solve that one? You can look it up, but you won't know the arm. So you have to have some thinking going on in your brain. So we look at the revolute frame. We can also look at the prismatic frame, right? So here we have this guy. So notice it's a different Q. So this is our Q right here for prismatic from the general. And this is the one for the revolute. This is our Q for the revolute. Which kind of looks
Like a rotation.
like a rotation, exactly what I'm going to say, right? Cosine minus sine,
I forgot what that's rotation.
sine, cosine,
Z, right?
about z. Yeah, kind of looks that way, doesn't it? So that's the prismatic version. That's a little bit different. What is that? That's a long z.
Mm-hmm.
We just kept the d. The effects of it. So that we can construct these Q matrices. Q matrices are always constant. And so the Qi, they represent the joint variables for theta I and di. Because theta I is revolute, because di is prismatic. And so we see these two Qs. So what we can do is we can perform what's called relative frame differentiation, where we can look at the partial differentiation of a frame that uses the transform chain and Q matrices to arrive at our Uij. The transform I is being differentiated with respect to only one Q term. And we can extend this to higher order derivatives if we wanted to. So we could use a complete T-frame and go through and manage all of these along the lines. The point is, everything we did in Lagrange works with this. You can see how we got there. I might have you guys work an example as a homework problem. I think that might actually be more beneficial. I'll probably give you two examples I want you to walk through on your own, now that we've had the full discussion on them. Is that fair? I think that would actually be a good homework. I've done that occasionally for this chapter, and I think it's a worthwhile endeavor, and it's as far as I care to go. I don't want you to get caught up in the math. There's no point to getting caught up in the math. That's what we did the symbolic tools for. If I want to have a calculus person just doing all the calculus and not understanding why we're doing the calculus, then great. You already took that class. Now you know why you took that class. So when you come to robotics, you go, oh yeah, I have to do the derivative of the arm, blah, 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 blah. Yeah, that's it. But again, let's go back to why the Lagrange is important. If I look at a problem, especially 6th degree of freedom robot arm, do I really want to do a free body diagram on a 6th degree of arm, especially if some of those joints are prismatic in the middle of them. And we've looked at a few of them, right? That's tedious. That's hard. That's difficult. Up front, Newtonian is easy. One joint, maybe two joints. That's a piece of cake. 5 joints, 6 joints with prismatics. Now, time out. That gets a little rough, right? So the Lagrange allows us to do that. And then we can look at the frames and their frame motions relative to one another when we differentiate the frames. And we can use this idea of this Q matrix in order to get us there. Make sense? Are we good? Do you see why I decided to lecture this the way I did? I'm glad I lectured it the way I did. Yeah, I think so too. So let's see, let's go ahead and launch. Now we can be more smart about things. Go back into Coppelius sim. So when you all saw 41 slides, you all freaked out, right? Well, we're only on 15. We're not going to finish. And here we are, we don't. Because I'm not going to sit there and lecture every line of the calculus. You can go from there to there. You've done that calculus already. I'm not gonna make you do it twice. You can understand and appreciate the theory behind it. So let's go to this guy here. You guys are working on your simulation right now that's like this, but not this arm. You're constructing your own arm or using some arms of your choice. How many guys have got your arm constructed so far?
Like in Capelli Sim?
Yeah, Capelli Sim. Yeah. So let's go ahead and run the sim. And now let's go ahead and look. Position's not as important. I'll leave that a little bit bigger. Let's look at torque. And velocity. And we need to pick and cover it up. We need 2 monitors. They need 2 monitors in here. I think we should all write a letter to the president. We need 2 monitors.
For projection screen?
I wonder if I you know the little pocket ones, right?
Yeah.
How expensive are those?
Like $50?
Those work, are those any good?
No.
You can get the short roll.
The T-Lose one are very good.
I got one from a friend when I first started dorming here. I couldn't even use it inside my dorm room.
Why?
It's so dim. Yeah, you couldn't see anything.
I mean, I'm sure if you're willing to put $100-200, I'm sure that would work.
Yeah.
That works. The cheapest option may not be your best option, but
You get what you pay for, what you're saying.
pretty much, yeah.
All right, well, let's go ahead and let's make this guy move. I can't cover that up too much. Let's move along. Let's try to move along X and Y.
I think you have the wrong two.
Yeah, you do have the wrong too.
There, now I think I'm right. Okay, so here's our torque. And so the one we're interested in, really, this one hasn't spun around yet. We're going to spin around, let's see, if I go, I think this one. Yeah. So we see massive amounts of torque right here on this joint right here, right? Now, what I want you to look at and watch what's happening, maybe make this bigger. Are these spikes. So I move up and down. So it's constant. Slowly going up. Slowly going down. But if I switch real quick, and I see that direction change, notice we get spikes. So the question is, why do we get those spikes?
The velocity.
No. What's causing these spikes to occur?
The instantaneous torque being applied.
Instantaneous torque. So
Because you didn't describe to Copelia how to do the acceleration. You're only controlling velocity. So you're like, I want to go from 0 to 100 now.
Right, that's why I have constant acceleration.
Yeah.
But when I change directions, I have a discontinuity, don't I?
Maybe.
Yeah.
I can't see.
So if I change directions, I'll get a discontinuity caused in that axis. Let's go ahead and change it again. Right, so it goes up, goes down. And that's when we get these two spikes. It goes
Yeah.
up, down, right?
There's that gap.
I wonder if I can change the mass right now. Should we try changing that mass? Let's just see if we change the mass of,
I don't think it'll matter.
I'll change the torque value.
It will?
Should?
Well, because in IK, remember, it does kinematics. It doesn't.
Yeah, I don't know, but no, it's still measuring the mass.
You might have to change the cuboid's mass on the bench.
Yeah, so let's see.
Primitive.
That's the one we want?
Yeah, that's the one you want.
Do we want to do?
You know it's the one you want because it's already enabled. The body dynamics.
No, I'm saying, is that the joint? Oh, the joint. So let's change the mass. Let's like make it, I don't know.
That should make a difference.
Should, let's see what
Yeah,
happens.
you like tripled it.
Let's see if it falls apart. No, that's a good sign. I need to find the right guy here. Destination. Now, if you remember how little it moved, I'm just gonna turn the velocity off. Go away. Yeah, I'm not even worried about that guy either. Yeah, definitely, right?
That's what this kind
Massively increased.
Obviously,
of disappear.
yeah, I can do this. Let me restart that. Stop this there. Did I grab the wrong one yet? Okay. Maybe the other one. Yeah, that's also the other one. So we can see there's a little bit of a profile right here that we start to get to that, right? Let's see what happens when we get there. But it doesn't really, when it stops and when it starts, otherwise it's pretty constant acceleration. So theoretically, at this point, it's almost like infinite, isn't it? So if my motor has enough torque, I mean, let's see if we can really break it. Should we try to really break it? Sure, why not? Let's really make that tip on that. Really,
Wait, can
really.
you click on the joint real quick? Click J5. Or no, J4 joint. Double click it.
Oh, you want to change the torque?
I just want to see what you have it set to, so we can figure out what will break it. 2.5 newton meters, that's pretty loud.
Yeah, it is.
You have to make it hefty.
So, 2.5. So let's go ahead and let's make, let's see, the really question is what is this one at, right? Let's see what that joint's at. 2.5 meters. I think all of them are 2.5. Yeah, I was playing the world's best motor.
Yeah, there you go.
Just because I didn't want to have problems later on. But let's make that mass very massive now. So let's go ahead and make this changing the mesh. Let's go ahead and make it.
Oh, you didn't save it?
You didn't exit out. That one's still on the mesh.
No, it's not still the mesh, because it's
That's the
already
right
loading
one.
is dynamic. You don't have to exit out each time, it updates just by clicking.
Oh, you might, did you change it when you had the sim running?
I did, yeah, so that's why, so it only changes.
While you were in the sim.
Right. So let's go ahead and make it,
Yeah, do that again, so then you don't have to remember, oh, it doesn't
no,
matter,
no,
you're
so I
not gonna
want
save it
this,
anyway.
I want this the way it is. Let's go with like,
There you go. That's a lot.
it's going to break, right?
Theoretically.
So the question is, how do I really know what this should be? Or is my robot capable of doing this? And the Lagrange will give me that analysis. Or I can sit here and play with it in Coppelius sim. See what happens.
First, probably see through both.
And we haven't moved yet.
I'm at the initial stuff. It's 40.
Yeah, it's like right underneath the mass. I have no idea what's going to happen.
Finds J5 position constantly.
Whoa.
Well, so in this case, Coppelia lets me do it.
You have an insane motor.
That's a pretty good motor, isn't it?
It's slowing down, it doesn't move as fast. but
Right, exactly.
It's still
So
moving.
it's still stimulation.
Yeah.
I said I have no idea what's going to happen because I've never tried that before. I just knew this was going to have an effect. But the bigger question is like this guy right here, right?
That's
This
J2,
is where it comes to a stop. When it comes to a stop,
discontinuity.
it's a discontinuity. Acceleration goes from something to zero. So is there a derivative at that point? No, the derivative is undefined. And so what we're talking about,
Why does it produce that?
this sweep in here,
No, like if it's undefined right there, why does it go more negative and not towards zero?
it's because of the direction it was headed.
Oh, it just continues its same, okay.
So that's why you see.
Oh,
right
to
here.
fake continuity.
Yeah.
That's
So
what
like
it's
this guy
doing.
goes way up here,
Okay,
then down, it goes down, then up, up.
This is based on the direction.
Right, the previous direction.
okay.
So the derivative is, it's a one. So the question is, well, what is it really? Suppose I had massive masses on there, and I can't account for that. So if I look at my third derivative, I can solve that, right? If I look at my fourth derivative, what if I controlled my second derivative so my third derivative could do a smoother acceleration? Or I can control my fourth derivative so that my third derivative was smoother. So I can control my fifth derivative so that my fourth derivative is smoother. You see where we're going with this, right? So I can construct a motion profile of each joint such that I can alleviate spikiness or my acceleration isn't too fast. I can decrease my acceleration, my rate of acceleration. I can control my rates so that I have nice smooth motion. Because we just saw, looking at all the Lagrangian, that everything is actually based on the acceleration. We started this course, position, velocity, acceleration. Now we're going to figure out what kind of motion profile should I use to the third, the fourth, and the fifth derivative from this point. Now we won't be looking at frames anymore. Darn. We're going to strictly look at, now we're going to isolate one motor. So we've looked at how do we get to that position? What is the velocity that gets this tip right here as we control each one of these joints? Right? We spent a lot of time on those two topics. We went through this Lagrange idea going, but I'm really trying to get the acceleration, right? So I don't go to an instantaneous velocity, I get to my velocity. But getting to that velocity, as we see right here, could maybe be problematic for my robot. I can't provide that kind of torque for it. So what kind of motion profile should I use in order to get there? That's what we'll talk about. So that's the next chapter. I will give you a couple of homework problems as examples I want you to go through, comment on, and understand. I'm not going to do the homework problems, the example problems for you guys here, because it's better, I think, as a homework problem for this point. Okay? Went through the theory.